Okay, let's go down to negative coefficient. For a negative coefficient, maybe this would look something like, there we go. So what would be the end behavior for this? Both going down, so we would write negative infinity and negative infinity. So now let's look at odd powered. If something's an odd powered function, you can kind of think of it being maybe like an x cubed kind of graph. If the coefficient is positive, it starts by being an increasing function. Some other crazy things might happen in the middle, I don't know what. But it also ends by being an increasing function, okay? And so its end behavior would be what? What would go here? Yep, as I go to the left, this goes to negative infinity. And as I go to the right, this would go to positive infinity. And then finally, let's do some kind of odd-powered function with a negative coefficient. This is flipped around. So as x goes to the left, this goes to positive infinity. And as x goes to the right, the function goes to negative infinity. So what I would like you to be able to do then today, and that was actually the question that Colin asked, right, is I would like you to be able to describe the end behavior without looking at the graph based on what you know about the function. So for example A, and you can always confirm graphically afterwards, but it is good to have us start thinking about, wait, what does this look like? What do you notice about this function? Some things that are going to help us decide. A positive leading coefficient and an even power. The even power tells me that the end behavior is going to be the same. It's going to either be up, up, or down, down. And it's going to be which one? Up, up, because this is positive. So I would write the limit as x goes to negative infinity of f of x equals infinity. And the limit as x goes to positive infinity of f of x equals also infinity. Okay, who thinks they know B already? If you think you know B, write it out. While you're doing that, I'm going to just show the first graph. Okay, so this has got some funky stuff going on in the middle, but still up and up at both ends. All right. This is degree 3, so it's going to have opposite end behavior. One is going to be positive infinity and the other is going to be negative infinity. The leading coefficient is -1. So as x goes to the left, what's the function doing? It's like this kind, right? It's going up. So I'm going to write infinity. And as x goes to positive infinity, the function is going down. Yeah. The leading coefficient determines in an even function. If it's a positive leading coefficient, then it's pointing up at the end. If it's negative, what happens? Is it going up anymore? they're both going down. Okay. If it's an odd-powered function, if it's a positive end behavior, think of it as like a cubing function going up. Okay. They're still opposites, but the left is negative infinity, the right is positive infinity. But then if it becomes a negative leading coefficient, that flips it over, and so then it flips those end behaviors. So it kind of just tells you, it doesn't necessarily match the infinity. I don't like to think of it that way. I like to think of it as how it changes what the function's doing. Like if it's generally increasing, doing some stuff in the middle, increasing if the function's positive or if the coefficient's positive, decreasing, doing some stuff in the middle, and then decreasing. Okay. Did I answer your question? Okay. Just a little snippet here. Those of you who are going to take calculus, technically in calculus we say this is end behavior, but normally a limit is a number that something approaches, and technically is infinity a number? No. So really, if we were in calculus, we would say the limit doesn't exist, but the function approaches infinity. But I'm just throwing that out there for those of you who will take calculus. Okay? We're going to write it this way, but in calculus we typically would not say a limit equals infinity because it's kind of a contradictory statement. Okay. All right, then let's move on to zeros of polynomial functions. So, a couple things that we should understand is what a zero is. Zero of a function is when the function f of x equals 0. Notice, am I putting 0 in for x? No. F of 0, if I put 0 in for x, that actually gives me the y-intercept. But when f of x equals 0, we call these the zeros of the polynomials. On the graph, these are called x-intercepts. So what are x-intercepts then? What are you looking for? Where they hit the x-axis. Another name you might have heard already before, or you might hear again, another name for these are roots. Okay, root, zeros, x-intercepts, those are all the same thing. They're all the same thing. Alright, example 2. We're going to do this without a calculator first. Find the zeros of the function algebraically. And so what we're going to do is we're going to set this function equal to 0. Miss Kay, can you grab that door for me? Thank you. Okay, so I have x cubed minus 16x equals 0. The only way that we know how to find the zeros of a cubing function is if we can factor it. So, can somebody tell me what or how can I factor that? What's my first step? Let's take an x out. Okay, so first I take an x out. That leaves me with x parentheses. If I divided both terms by x, because that's what factoring is, it's division, what would be left? X squared minus 16 equals 0. And then I can go one more step. This is the difference of squares. What does x squared minus 16 factor into? Good. X, so I'd leave that x in front. X plus 4x minus 4 equals 0. How does that help me find the zeros then? We did this in chapter 1. Set all three of these equal to 0. Zero product property says if I have things that multiply to be 0, then one of them has to be 0. So I set x equal to 0. I don't have to do any work there. So one of the x-intercepts is going to be when x equals 0. I set x plus 4 equal to 0. What would x be in this case? Good. So one of my zeros is there. Alright, and then I do x minus 4 equals 0. Alright. So this has 3 zeros or x-intercepts. They occur at x equals 0, x equals negative 4, and x equals 4. Go ahead and now put in your graphing calculator and confirm that's what you see on the graph. Okay. Now, I don't know the tops and bottoms, right? I could zoom out if I wanted to, but oops, I just zoomed in. Okay, there's a little better. You can hopefully see they cross. Here's a -4, here's 0, and x equals 4. Okay. If it's quadratic, somebody asked me this today, just sidebar. Hold on, where can I put this? The first one, like I asked in the homework, was something like this. I'm making this up in my head, so bear with me. Okay. If I said find the x-intercept of that, how do you factor that? What does this factor into? Yep, x plus 1 equals 0, x plus 6 equals 0, and then you could go from there. All right. Next topic. Next